Hi, and welcome to this session in which I will do an introduction on how to optimize and measure performance on AWS Graviton processors. I'm Arthur Petit-Pierre, a Graviton principal specialist at AWS, and I'm going to present you a couple of things about the way to think about performance and how to optimize performance on Graviton-based instances. The first thing I'm going to cover today is knowing a little bit more about the architecture. And I've actually structured this presentation with three parts. The first one is going to be about the architecture of the Graviton processors. The second one is going to be about a couple of best practices with to performance on Graviton-based instances. And the final one will be showing you a methodology to measure and analyze the performance on Graviton-based instances. So let's start with that first part. First thing is we have two types of Graviton-based instances. The latest one is Graviton 3, the previous one is Graviton 2, and there are a couple of differences between the two. We've made Graviton 3 a little bit wider in terms of how it fetches and decodes the instructions, so it can bring more instruction at every clock cycle, and it's also wider when executing the instruction set. So we moved from a 8 wide issue units to 15 wide issue with a larger instruction window. There are a couple other things that we've improved with Graviton 3 compared to Graviton 2. The first one is we have doubled the size or the number of vector registers for SIMD instructions. There are two ways to access those registers now, either through the legacy ARM64 SIMD architecture, also called Neon, or new generation of vector instruction called SVE. A couple additional floating point formats have also been introduced with Graviton 3, including bfloat16, which is a good way to improve the performance of machine learning types of workload. We've also improved the memory subsystem on Graviton 3 with more units to do loads and stores, improving the memory performance. We've doubled the number of multiplication units to be a bottleneck for RSA signature on Graviton 2. So that thing has been vastly improved on Graviton 3. And a couple additional new features that we've introduced in Graviton 3, we now have pointer authentication, which is a way for the processor to sign pointers and check them before dereferencing them, a pretty interesting security feature. And we've also added instructions to generate random numbers. A big difference that we have when considering Graviton 2 and Graviton 3 processors compared to Intel processors or AMD processors is that we are not implementing simultaneous multi-threading with Graviton-based instances. On Intel processors, we have simultaneous multi-threading, which means that when accessing AWS instances, for each of the vCPUs that you get access to, we are mapping the vCPU to a thread on a physical core. The consequence of that is that you have those two hyperthreads that are mapped to a single physical core, so they share part of the physical core. And instead of getting twice the performance of what you would get with a single vCPU, when you use two concurrently, you're rather getting like 1.4 to 1.6 times the performance of a single vCPU. On Graviton-based instances, on the contrary, we've chosen a different design. No simultaneous multi-threading. Every core, every physical core is smaller, but we have more of them, roughly twice the number of them. And each of the vCPUs is mapped to a physical core. The consequence of that is that we scale better on Graviton-based instances. And when you're running the same workload on two vCPUs, you get exactly twice the throughput of a single vCPU, because they're no longer sharing any context, they're no longer sharing resources, and you really scale linearly by the number of vCPUs. It has consequence on benchmarks. If, for example, or performance analysis, if you're running an application that is single-threaded and you try running that on an otherwise empty system on an Intel-based instance, you will usually get a pretty good performance. And if you compare that to the same application running on Graviton, in some cases, you will see the Graviton version running slower. Now, if you are doing the same test with two instances of that application running at the same time, loading the two hyper-threads, and do the same on a Graviton-based system, you will usually see the Graviton system performs significantly better and scale significantly better compared to the Intel system due to that higher number of physical cores. So pay attention to that when running benchmarks. At the memory and the interconnection system, Graviton 2 and Graviton 3 are actually pretty similar. They offer the same number of cores, up to 64, that are connected together through a mesh that connects them to 8 memory banks using DDR5 Graviton 3 or 4 on Graviton 2. And the memory on both systems is fully encrypted and in real time. We document all the features that are available on Graviton 2 and Graviton 3. I will show you later in that presentation a link to the Graviton Getting Started guide. The Getting Started guide contains a lot of information, super interesting to have a look to. One question that I get often from customers about Graviton-based instances and processors on AWS is, what's the size of the different levels of cache? How are they accessible? Those kind of things. So it's part of the documentation, and I have it on the table that is shown in front of you right now. But actually, all those information are available when you're using Linux. There's a command called lscpu that you can use. It will actually read a certain number of entries in the pseudo file system /sys, and we'll get that information for you because it's exposed by the kernel. So every time you wonder about how many NUMA domain there's on an AWS EC2 instance, how many cores are available, what's the level of L1, L2, last level cache on an AWS EC2 instance, well, you can actually figure that out yourself. It's fully exposed to the operating system, and for every operating system, there's a command that would allow you to read those information. So here's the one you can use on Linux. Now that you know a little bit more about the Graviton architecture, let's talk about a couple performance best practices. So let's start with a question. Do you remember when Graviton 2 was announced? I do, because I was there, and I was already looking after customers running on and trying to adopt Graviton-based instances at that time, and that was on December the 3rd in 2019. Why is that important? Well, it is pretty important because if you look at the various components that you might have on your software stack, some of those components are way older than Graviton processors. If I take, for example, RHEL 7, RHEL 7 was released, the initial version, in 2014. OpenJDK 8, that's the same thing, March 2014. I've seen some customers using GCC 5.4. That's actually, I think, the version that you would find on Ubuntu 16.04. Well, that version was released in 2016. I've got requests from customers to use Python 2.7 on Graviton-based instances. Well, the version was released in 2010. There's absolutely no way that those different software components would be optimized for Graviton. which was only released in 2019. So a very simple rule when you're starting to adopt Graviton-based instances is please start with a software stack that would be as modern as you can afford. If you're using an old version of a Linux distribution, migrate to a more recent version. If you're using, I don't know, let's say Ubuntu 14.04 or 16.04, well, you'd better upgrade to something more recent. Ubuntu 22.04 will give you really good performance on top of Graviton-based instances, way better than an old distribution. And the same is true, obviously, for any Java runtime version. You would also get better performance if using a more recent version of GCC to compile your application. So you got the message. The first best practices when adopting Graviton-based instances would be start with a modern enough software stack. If you're running on legacy stuff, it's going to be hard to get the level of performance that you're targeting. One place actually where you can find a lot of documentation on what are the right versions to target is the AWS Graviton Getting Started guide that we host on GitHub. The guide has been assembled by the Graviton team. It's designed to help you with transitioning to Graviton and optimizing your application. So it covers a ton of different areas, including various languages and libraries, tips and tricks for those languages and libraries, how to compile your application the right way, what versions we do recommend, links to various blog posts and explanation, those kind of things. Don't hesitate to use it. And again, one of the recommendations that you will find on this guide is that we really recommend using the latest versions of operating systems, compilers, and languages runtime so that you could get versions that have been truly optimized for Graviton processors. A couple examples. If you look at the Java section of the Getting Started guide, you will see that the minimum version is, recommended version is Java 8. That's the first version that would have an ARM64 version. So before that, there's just no way to use that on a Graviton processor. The recommended version, however, is at least 11, because we know that with Java 8, it will run for sure, but in some cases, you're not going to get the best level of performance. However, if you can afford to go with something more recent than 11, that's even better. If you can go to 15 or 17 or more recent, you will most probably see even better performance on Graviton-based instances. Well, the same is true actually for x86 instances also, but it's even more true for Graviton. If you can use Amazon Corretto, which is the Amazon long-term supported version of OpenJDK, it's even better. It's not just because that's from Amazon. Well, that's a good reason. We are providing support for free on Amazon Corretto, but we do more than that. We also do compile Amazon Corretto, ensuring that you get the best compilation options for Graviton. So by using Amazon Corretto, you can ensure that you will get the best built version of OpenJDK. That being said, the goal for Amazon is not to diverge from OpenJDK. Everything that we are doing in Corretto is sent back to the OpenJDK version, the community version, so that the compatibility is not broken, and every improvement that Amazon is doing for Amazon Corretto benefits also to the OpenJDK community. If you want to know more about our recommendations for Java, please have a look to the URL that is at the bottom of the screen. There's plenty of information on how to configure your JVM on Graviton-based instances to get the best level of performance. Another example would be how to use C or C++ based application on Graviton. The Graviton 2 and the Graviton 3 processors are offering a really recent version of the ARM64 architecture. Graviton 2 is using the Neoverse N1 architecture. Graviton 3 is using the Neoverse V1 architecture. And so your application will tend to perform better if you're using a specific target when compiling the application. When compiling for Graviton 2, you can use minus M CPU equal Neoverse N1. Forget about the star on the slide. That's just Neoverse N1. And that will generate code that will take into account the specific instruction set that I've been introduced for the Neoverse N1. The code generated with Neoverse N1 will also run on Graviton 3 and will be well optimized for Graviton 3. So if you plan to use both Graviton 2 and Graviton 3, that's a good option. If you plan to only run on Graviton 3, though, you can go further than that and use minus M CPU Neoverse 512 TVB. And that option will also take advantage of some of the options that are available on Graviton 3, but not on Graviton 2. Things like SVE, things like the random number generator, instruction set, things like pointer authentication would be available for Graviton 3, but not for Graviton 2. Be aware, though, that when compiling with minus M CPU Neoverse 512 TVB, you might generate code that can't run on Graviton 2. So if you're targeting only Graviton 3, that would be the option to use. If you want to target both, stick with minus M CPU Neoverse N1. In terms of GCC version for Graviton 2, the first version to be to support the Neoverse N1 architecture would be GCC 9. For Graviton 3, that would be GCC 11 and above. But in both cases, if you can afford to use a more recent version, if your Linux distribution is giving you a more recent version, you will most probably see better performance. Again, same as for Java. Please have a look to the Getting Started Guide section on C and C++. There's a bunch of other information that are available here, things around how to ensure that you're using atomic operations for Graviton 2 and Graviton 3, those kind of things that can make an application faster. Now let's go to our third part of that introduction to performance and performance analysis on Graviton-based instances. So let's talk a little bit about micro benchmarking and a thing that I call often passive benchmarking and why it won't help you, or at least not initially. Something that I get pretty often from customer is they want to know how Graviton compares to, let's say, whatever Intel-based instances in the AWS portfolio by using a certain number of predefined benchmarks. And those predefined benchmarks tend to be what I call passive benchmarks. It's running something, collecting data, and not really analyzing anything. And well, the reality is that it's really, really hard most of the time to draw any conclusion from those benchmarks and to get from those how any given customer application is going to behave. Because there's more at stake than just that specific benchmark in your application. You're using totally different libraries. You might be doing things that are pretty different. And it's often way more useful to do active benchmarking with your own application, which means analyzing the performance of your application while it's running on AWS instances and trying to understand what are the bottlenecks, what are the differences between two instances, and what can be optimized. Micro benchmarking is still really useful when you want to know what is the maximum you can get from a given subsystem, That's where it starts to be interesting. Things like, okay, what's the maximum memory bandwidth I can drive? What's the floating point throughput, the maximum floating point throughput that I could get? Because that gives me a ceiling about how high my application could go if I was fully utilizing one of those subsystems. But a collection of characteristics like the memory bandwidth, the floating point throughput is going to tell me little about my application unless I have a really, really well-structured model that will tell me exactly how it behaves depending on those different inputs. And very, very few customers have those kind of models, if at all. It tends to be way better to be able to ask you the right type of question. An example of a wrong type of question would be, how do Graviton instances compare to x86 based ones on Java? That's a super broad question. Java recovers so many different applications. Some of them are going to be CPU bound. Some of them are going to be memory bound. Some of them are actually just moving data around, and they mainly depend on the network. So that's a super broad question, and no benchmark is going to answer you how do Graviton instances compare to x86 based instances on Java. A better question, and something that is closer to what you can actually do, would be, how does a Graviton instance request throughput compared to current instances on my Java application at a P99 of 10 milliseconds for a mix of 60% gets and 40% puts on an Ubuntu Linux 2004 LTS distribution? That's a really narrow question. We have a definition of the software stack, we have a definition of the workload, and we have a definition of what we are running on and what we are comparing with. And that's a really interesting question to answer, because while answering that question, we can also analyze the behavior of the application, understand what's slow, what's fast, how close we are to the limit of the infrastructure, potentially understand whether we are using the right type of instances. I've seen many customers guessing that they need to use the high network throughput instances, while in production, in reality, they were using 20% of the network bandwidth. Or I've seen customers telling me that their constraint was the memory bandwidth, to only later discover that actually they were bottlenecking on disk I/O. So doing active active benchmarking to answer a really narrow question like that one is going to bring you a lot more value than trying to answer pretty broad questions. To answer those kind of questions, the AWS Graviton Performance team has developed a Graviton Performance Runbook that is part of our Getting Started guide on GitHub. The URL for the Performance Runbook is displayed at the top of the screen, and it covers tools and best practices when doing performance analysis on Graviton-based instances. The large idea of that performance runbook is to start by defining a benchmark, a narrow enough one, similar to the second question I've shown you and not to the first one. The second step is to ensure that you have the right system to measure and the right system to put a load on top of that system and measure its performance. It goes through different steps to verify that both the load generator and the system under test are configured the right way, and then guides you into understanding what are the slow path, why the application is or is not behaving how you would expect it to behave, and finally suggest a certain number of optimization that you can apply to get your application to go faster. So let's have a look at some of those steps in more detail. Of course, when doing that for your real application, I invite you to go to that GitHub version of the Performance Runbook. There's a lot of details there. We highlight all the steps, step by step, with command line and helper scripts. That goes a little bit too deep for the short introduction I'm doing today, but I'm going to highlight the high-level steps. So the first step is to define your benchmark. Two things here: the system you're going to test, so that's the type of instance, the software stack on top of it, the version of your application. And the second thing is defining how you will drive the load on the system. Defining a load point that could be the maximum throughput, where you do not care about the latency, you just try to get the maximum number of requests through the system, or the throughput at a breaking latency. Many systems exhibit a behavior where until you start maxing out the resources available on the system, the latency will stay pretty low. And then at some point, you will max out some resources. It can be CPU, it can be the memory bandwidth, it can be the disk I/O. And at that point, the latency will start to degrade. And the latency for many systems is the thing that matters to your user. That's what they will see when loading a page, when launching a request. That's the time between they launch it and the time they receive the answer. So up to a certain point, you will be below your SLO. And when you reach the breaking latency, that's where it will start to be bad for your users. So determining what is the throughput that you can achieve at breaking latency is really key when evaluating the performance of an instance on AWS. The second step in the performance runbook will be to configure your load generator and your system under test. On the load generator side, among the things that you really need to ensure is figuring out whether you can drive enough traffic from your load generator. In some cases, it means choosing an instance that would be large enough or that has enough network bandwidth. And also, I would definitely recommend ensuring that the system you're using is far enough from its own limits not to generate noise when measuring the performance of the system under test. The closer you will be to the limit of the system, the higher the chances that it might generate noise and prevent you from getting the information that you want to get about the system under test. On the system under test side, ensure that you're comparing the same setups. I mean, the same version of the Linux distribution, that you have configured systems the same way, that you are not using a newer version of a library on one system compared to the other. Try to minimize the differences between the systems. Before starting to measure the performance and analyze what's going on, also check and fix any errors or limits that you're reaching so that you would not be analyzing an issue instead of a performance limit. Step 3 will be analyzing the performance. The first step when analyzing the performance will be to understand what part of the system is slow or saturated. A method that I love here, and we use a version close to that in the performance runbook, is the use method that has been invented or made really popular by Brendan Gregg, which is that for every resource on your system, you will first start by checking utilization, saturation, and errors, so that you would understand which part of the system is close to its maximum utilization and whether it is saturated or making errors. Lots of tools can be used in that area. in the image at the bottom of the screen, there's a long list of tools depending on which areas of the system you're stressing. And Brendan Gregg is making available on his website a long list of the tools that you can use and how to use them on Linux to determine whether your subsystems are saturated or generating errors. For the next step in the performance runbook, we will be using under the hood a tool called Linux Perf. Perf is an event-oriented observability tool that can help you to analyze what's going on your system, do advanced performance analysis, and troubleshoot the behavior of the system. It has a website on perf.wiki.kernel.org, and on the right of the screen, you can see various places where it can help you analyze some counters. So the step 3 in the analysis journey will be to analyze the performance and understand what part of the code is slow. There are several different ways to do that. A first way, when you see that your application is maximizing the CPU utilization, and so you're pretty confident that what you want to analyze is a CPU utilization problem, is to do an on-CPU profiling. To do that, on the perf runbook, we are providing you with a couple of wrappers that are using perf under the hood to do a perf record that will collect the traces and then build a flame graph from those data. Ensure that you're running for long enough to get a meaningful collection of traces. Duration around 10 to 20 minutes are usually considered to be the minimum, so that you would get enough information to do the analysis. Once trace collection has been done, you can generate a flame graph. A flame graph is what you can see on the right side of the screen, where the time spent on each of the functions run by the application is graphed depending on how frequently and how long they're spent on CPU. It is really convenient to generate those graphs and use them to analyze the differences between what you see on Graviton-based instances compared to what you see on other instances like the x86 instances you have on AWS, and see whether there are parts that are slow specifically on Graviton that would give you the opportunity to analyze and optimize. If the application, on the contrary, is not maxing out the CPU and you want to understand where it is spending some time not on the CPU and what it is blocking it from maximizing the CPU utilization, in those cases, you can do an off-CPU profiling. It's a little bit more resource consuming, so usually not the first thing that you're doing, but same thing, it will allow you to generate a flame graph and understand what are the part of the application that are stuck out of CPU waiting for something else. That could be I/O on the network, that could be I/O on the disk, those kind of things. Once you've exhausted the ability at the CPU level, and for example, when you would observe that your application is uniformly slightly slower in the on-CPU profile with no obvious hotspot, it can be due to a hardware slowness. So places in the CPU where you would actually run slower than expected. That requires to measure contours at the CPU level to understand the bottleneck, whether you're bottlenecking because of cache misses, because of memory bandwidth issues. We have a fully detailed methodology on how to do that on the Graviton Perf Runbook that we host on GitHub. The URL for that is available at the bottom of the screen. That's a little bit too long for the introduction that we are doing today, but I would really invite you to have a look there and see how much information it could give you for your application. The full performance runbook is available on GitHub. If you have used it, and if you still can't find the root cause for your issue, what can you do next? A good way is to contact us at ec2-arm-dev-feedback@amazon.com. Both the Graviton performance team and the Graviton SA team is behind this address, so we can answer you. Or you can also talk directly to your AWS account team and get additional help. Thank you for listening today. I hope you've learned a couple things from that, and I wish you a happy Graviton adoption journey.